It's 3 times 10 to the minus 9. Let me show why. At the minimum, both contributions are equal. I'll explain why that is so in a second. So we find that the constant c times the value h minimum equals the constant d times epsilon over h minimum, from which follows that h minimum is the square root of d epsilon over c. Epsilon is multiplied by a factor of 10 to the minus 9, which means that the value of h min for double precision is multiplied by a factor of square root of 10 to the minus 9. Starting from the value of h min for single precision, we have to multiply by a square root of 10 to the minus 9. In total, this is 10 to the minus 8.5, and that's about 3 times 10 to the minus 9. An important remark: this model was made for the forward Euler method. If you have a method of higher order, if we have ch square or even ch4 in here. So from this result we learn that as we go from single to double precision, we may be using a step size that's about 4 to 5 orders of magnitude smaller, and hence the error will be smaller by 4 to 5 orders of magnitude. The price that we would be paying is that we have in the order of 10 to the 4 to 10 to the 5 more computation, which looks a little prohibitive. But then again, with a method of higher order, you need far fewer steps than with the forward Euler method. So the effect of round-off errors tend to be way smaller with more advanced methods. In case you're interested, let me explain why these two contributions are equal at the minimum. Otherwise, skip over the rest of this video. Substitute the step size, h, by e to the minus u with an appropriate value of u. Then the total error becomes c times e to the minus u plus d epsilon e to the u, because we are dividing by that power. Now you can see that the first part becomes a falling exponential function, and the second one becomes an increasing exponential function. Both fall, and due to symmetry, the minimum has to be where these two curves meet. A completely different approach to that problem is, of course, to compute the derivative and set it equal to 0.